I'm Alex. I work at Satora for 4 years now. Dev architect something. Yeah, and I'm gonna talk about timeouts and especially how to solve them. Okay. Okay, so I start with an overview of the talk. I'll start. Why do we even have timeouts, right? There are so many apps there, none of them have timeouts. Why does Satora Approver have timeouts? So I'll give a bit of background, a little of the computer science view of it. Then after this short detour into theory, I'll be more practical and talk about typical causes of timeout, and then for these causes, kind of matched strategies that one can apply to get out of these timeouts, to get your rules out of these timeouts. And then I'll show what the Satora prover actually does. So this is very work in progress, but we're working that the prover can actually help you with the diagnosis here by analyzing the rules that you gave it a little bit, for example. And then I'll go through a few concrete examples, like case studies where we have a timeout that looked so-and-so and what we did about it to make the rule pass or show a counterexample. So just to give a little teaser, so I'll show the meaning of, in your reports, you have this green highlighted here button that gives you this view here, and I'll show you what it means, and it's supposed to do all that, what I said. And also, right at the start, a disclaimer. So first of all, I'll say this a few times. This is not an exact science, what I do here. Formal verification is an exact science, but timeout mitigation is not. We'll also see a little bit why. And also, many timeouts you could think, well, why isn't the prover solving this? And yeah, we're working hard to make the prover timeout less, and we have worked hard. I think there's been good progress. But many of these things are also for right now, right? So the prover is at a certain stage of its development, and we're having techniques that are supposed to help you right now before the next feature has landed. Furthermore, it's an experience-based thing. So feedback, there will be feedback loop between the mitigation, the strategies, and using them and applying them to actual timeouts. And also I want to stress that I'll show a few statistics and heuristics about timeouts. I think they will be, as all metrics, they're never complete. So they should never be the only governing principle. So I'll give a metric for the size of your program, but just you should never optimize for metrics. You should always look at the code and use the metrics to help you with that. Yeah. That just as an early disclaimer. Now, getting right into it in terms of background. So maybe you've seen this picture, maybe not. So this is the very high level zoomed out view of the Satora prover. So it's the Satora prover is a little bit like a compiler. So except that it doesn't compile to executables, but to logical formulas. And the format of these logical formulas is called SMT. So what it ingests here on the left is Solidity files and CVL spec files. And then it compiles them into our internal intermediate representation called TAC. does a lot of transformations and optimizations, and then ends up with a formula. Then we have a program called an SMT solver that solves this formula, meaning it says whether it's satisfiable or not. In the satisfiable case, it gives a model for the formula, which we then translate back into a report. So the formula is in terms of, well, the model is in terms of formula, but the report is back in terms of solidity, or as close as we can get. Yeah, so now let's see. So in terms of timeouts, actually, the most interesting part is the SMT solving here. And we're using external tools for that. So C3, CVC5, Yikes, SMT Interpol, and more are prominent examples. Those do the formula solving for us. And usually we don't want to look inside them, but here, for these purposes, it's nice to look a little bit of how such an SMT solver is structured. And this is right from the C3 documentation. So inside, and I won't go too deep, but just to give you an idea of the problems that it solves. So the core of the formulas we're giving is, you can always look at them as a propositional formula. So propositional is when you just have truth variables like A and B or C. And the SAT solver part, that's one part of the SMT solver, but then the SMT solver also has to understand things like arithmetic. So when it's not just A is true or false, but X equals 15 is true or false. So it also has arithmetic solvers and for arrays and bit vectors and data types, etc. And an SMT solver works in a way that it always starts at the SAT level and then asks the theory solvers if they agree. So it will kind of run back and forth between these parts here. And now, looking at these parts and what computer science says about them is solving SAT is NP complete. I say in a minute what that means. Solving just the conjunctive fragment, so only so if we've solved SAT already, and then we just look at linear integer arithmetic, then we're still in NP complete. In case of nonlinear, we're undecidable for the integers. Arrays, and it goes on like this, right? So NP complete, if you haven't heard the term, it's I'm going to be very pragmatic and translate it to exponential, or worst case exponential. And exponential, people think about it as soon as your problem gets just a little bit too big, you get into runs times that are totally unacceptable, like 100 years or I don't know, to the end of the universe or something like that. So exponential is usually too hard, kind of, to be practical. So theory kind of has these, I don't know, downers of statements, right? And we're even combining these parts, right? But to set that off, I want to tell a little bit about history, and that's of SAT solvers. So SAT is a very famous problem in computer science. It's satisfiability of propositional formulas, and people had algorithms in the 60s. In a way, they're still used. This result that it's definitely hard in the worst case is from the 70s, and then in this very simplified history, not much happened for 25 years. People were put off. But then since the 90s, SAT solvers have made huge progress and have moved into industry. Things are possible now that people thought would never be possible, like solving SAT problems with millions of variables. And they're actually used in industry, like for hardware verification, for example. So what do we conclude from this? Even though we work in a high, well, difficult complexity class, says theory, there are still many parts of it, right? The theory is making very broad strokes here. And if you look closer, there are still many problems inside there that are solvable and that are very useful to solve. So, and I think Satoru Prover shows this every day, right? But there is this open challenge of robustness. So that's also unsolved for SAT solvers, and they're still used in theory. And robustness means that even small changes in the input can change the runtime a lot. That's just how it is. But that also opens up kind of the game the timeout mitigation discipline, so to speak. It means that timeouts can happen and will happen on certain rules, but often there's a little tweak that allows you to push it from runs for practically ever into solves it in minutes. So that's kind of what we're setting out to do here. So, and I'm emphasizing that this has a lot to do with experience, right? Because if it was an exact science, we'd make a better algorithm. So this is kind of the first background part. Feel free to answer questions, right? Now or later. Now I'm getting into the more practical. So what can we do, right? So this slide is in a way very basic. So what can we change? We can change the input. What are the inputs to Satoru Prover? There's the configuration. So the configuration flags you're giving, or in the conf file, there is the specification, the CVL files, and there's the code. So of course, these options get increasingly worse, right? So we don't really want to change the code. It's kind of a last resort. But sometimes you can still get much better results than, no results at all by that. And then I'm going to talk about tools that help us do this, like especially to help us find what of these options we might be good to take and where. And again, first, a good understanding of code and spec is important. But then we're also developing tools that I'm going to show, which is the timeout tech dump. I had this preview. Helps you by giving a graphic view and some statistics, even more statistics, timeout cores. This has preview characters, so we'll that isn't on current master, but we're developing. So now let's look a little bit closer into classes of reasons for timeouts, like. So in order to understand the timeout, it's helpful, right? So this is not the only view we can take on what makes the problem hard, but we can use this understanding of the SMT solver we have, and like find a few causes or like a few ways in which our input to the solver can be difficult. So for example, there's path count, right? So our program, if you have branching, you double the paths, right? If you have branching in sequence, you double the paths each time. And this leads to a path count that we display, I'll show later. And this ends up heavy on the SAT part of the solving. There's hashing, also the SAT solver map more or less. There's arithmetic. That's kind of a different part of the problem, right? So, and that's, and especially nonlinear is bad. So that will end up in this arithmetic solver. There is something like if you have many reads and writes from memory or storage, that can add complexity. That's kind of the array solver, which is it's kind of a separate part of the solving. the quantification also ends up in that array solver, and bitwise, it depends a bit on how you run the tool where it ends up. So this is just a vague, categorization of things, how a formula can be hard. Now, getting from this, we can match these with again, this table is very, just to give you an idea that, so this will be work in progress, and we will have a documentation page matching these better and giving many more ways. But what I'm trying to say here is that there is a rough matching between candidate reasons and mitigation strategies. So if path count is heavy, then we can talk about splitting options. I'll show an example later. In the spec, we might want to apply summaries. For example, a non-net summary of a function that contributed a lot to the paths. Well, we'll remove those paths. We'll get the path count down a lot, and thus ease the burden on the SAT solver. Yeah, and in the code, basically similar to summary, right? So you might be able to make it ignore certain parts if you're sure they're not relevant for the verification, for example. For the nonlinear arithmetic, solver choice is actually, so that's an option, but which SMT solver, they're all good, but at different times. So that's something to play with. Again, summarization, in the extreme case, make things linear, but also computations. We'll see an example. And so on. I'll not read the rest of these, but they can be there for reference. I think it's probably more instructive to look at examples. And we can revisit later. So now let's talk about the diagnosis part. So as I mentioned briefly, tag is the name of our intermediate representation. So we're kind of going into the guts of our pipeline a little bit. And yeah, so it's getting perhaps a bit technical to look at, but I'll try to give a very pragmatic overview without such that you can use it without going into needing too much understanding. So the tag can be accessed by this button that I mentioned before. So it's always you have to click in the report, you have to click on a rule, and then both in the violation, not violation, timeout case, this button should be available, but it will display different things in each case. So in the counterexample case, it will show you actually the call trace, but a different view on it, on this tag level. In the not violate case, it can give you answered cores if you've activated them. And in the timeout case, we'll look later. Yeah, so one thing about the tag is you've seen it a little bit. So this is a good and a bad thing, right? So it's very close to the SMT formula. So it's still a program, but inlining, summarization, all kinds of optimizations, they've all been applied. On the one hand, this makes it tricky to match to the Solidity code you had, but I'll give hints. But on the plus side, it also means that if you think something has, like you've summarized all nonlinear operations away and they show up in the tag, then the summary hasn't worked apparently. So, or something else went wrong. So in a way, tag speaks truth in terms of what actually ends up in the formula. So yeah, that's the button. Yeah, I think I've basically said that. So yeah, so let's jump right in. I say okay, let's look first at the program. So this is a very silly program that I wrote just for illustration purposes. So or a rule. to be more precise. So all it does is it has a little bit of control flow, right? And if this Boolean B is true, it will call the function foo, and otherwise it will call the function bar. And the contract has a field, has a public field X. That's a uint. So the contract looks like this. So it has this field and a foo that increments X twice in a bar. It doesn't really matter, right? So just some dummy code. So, but what does this look like in tag? So that's this. So first of all, tag has this, the tag view or tag dumps have a graphical display of the control flow of the program, right? So in the program, we saw there is a branching, if and else. So in the control flow graph, you can see this as a split, like control flow goes either into the then or to the else branch. Then we can see here, that's how method calls look like in the tag dump. And then control flow joins again, and there's another method call to the scatter to X, and then we finish. And also these control flow graphs, these dotted call nodes, they're kind of, so in the real tag that we have, things are inline, but for easier viewing, we kind of hide this inline subgraph under such a call node. So if I click on this, I get the very simple control flow graph of the bar function, which only has one node. And that node has this code, right? So this doesn't look very pleasant, but a lot of it is scaffolding code, right? So so I don't think it's very helpful to look at every single statement here. So the main takeaway is you can orient yourself in these tag programs, first of all, by the calls, and second of all, by hovering over these lines that have this dotted underline. So we're trying to have as many as we can of those. And these dotted underline, they give us source pointers. So you see this red hover. I can't point it with the mouse pointer, but it says in our Solidity code in line 9, there is this x+1. And apparently this, we can see here is an addition. So this was generated from that. And this is like the, yeah. So basically these give you an idea where in the program you are. Yeah, and I mean, of course, I could tell you more about it, but I don't think it's worth it. I think this high-level view of tag should get you somewhere. So we'll see more in the actual timeout example. Yeah. And I should say these calls that we're seeing, it's only external method calls, not internal method calls. Internal method calls just look like inline code, the tag. So now let's look at the timeout dumps. So what we just saw was a counterexample dump. So that highlights the call trace and gives you also, the box on the right gives you the values of the counterexample. But the timeout dump looks a little bit different. It looks more colorful, and it has this explanation box, which also, if you scroll down, has some extra statistics. Yeah, I'll dive right into the demo. So we're interested in this rule. So we see in our usual report, we have this rule has a timeout. So we click the dump button. And what do we see? Well, it's again a tag graph, but it's been colored. So basically, there are two classes of coloring, so to speak. So first of all, there is the orange, yellow, green. and that refers to what we call splitting. So internally, Satora Prover tries to, I'll have a better explanation later, but just as a high-level overview, internally, Satora Prover tries to cut the control flow graph into sub-problems, kind of, and then put the results together back again. And this orange, yellow, and green gives us information about how the splitting behaved and which results came back from it. And then, perhaps even more interesting, is this violet color. So it's combinable with the others, but mostly with orange. And that basically is where we heuristically highlight nodes in our program that are hard. So let's look at this one. We look in more detail. Yeah, actually, it's good to briefly look at the code that we have here. So that I want to show later, actually. But let's look at the rule. So it's this somewhat simple rule. We deposit and then we redeem, and we want that no one can profit off of that. You don't need to read more. We ran this, it led to this timeout graph, and now let's look at it. So here we see the deposit call, here we see the redeem call. And very pragmatically, let's look for the violet color. Call nodes that have violet nodes in them are also violet, so that you can let yourself be guided from the top, basically. And then we find this node. So this node also has highlighting in the code, and it has this kind of headline, difficulty headline, and it says, oh, this block was highlighted because we have 3 divisions and 4 multiplications in it. And none of them are obviously linear arithmetic, like with constants or so. So we see this, and then we actually look out. Now we're a bit unlucky, right? So it's not immediately clear. We're kind of somewhere in this deposit call. But luckily we have pointers, right? So it tells us this is in math.sol and it's a division. This is all in math.sol, all basically consecutive lines in some source code file. So we look, let's look at the source code. So I have this math.sol open, and the line numbers were something with 120 or so, starting earlier. And then I see that I'm in this muldiff function. And this muldiff function is a very smart function. It computes something very simple, x times y divided by denominator, but it's smart because it does it with full precision, right? So it is as if this multiplication can exceed the 256 bounds, and we're still precise in that sense. So it does a lot of computation and a lot of nonlinear. So by our standards, these number of multiplications and divisions is significant. And yeah, so that's likely our timeout culprit, because it doesn't only occur here, but it also occurs here. So we see, okay, this is again the same function. And then we look some more, and yeah, that's all the violet. Just to give a TLDR of what the orange means. So the orange means this is the subproblem that we've actually timed out on. So usually it's a big part of it. So the yellow means that has been queued for processing, so we know even less of it. It might be very easy or it might be very hard. But for the orange means that's actually part of the timeout reason. And then there's the green. Unfortunately, that's not so much here. That means that we've solved. So the solver has already a result. Whatever visits this, whatever happens before or after, we're done with this. We already have a proof for this. No violation can ever happen when we're looking at a path that takes this node. Yeah, so this is so this was probably much. Are there questions at this point? Otherwise I can go on. Okay, I'll go on. We can of course also revisit later. This is it. So I'll go into a bit more detail about the splits and all that stuff next. But this was kind of like the short way to the timeout reason, and I'll also show how this story continued in this practical case. So I'll have the case studies later, and I show what we actually did in order to solve this. But first, let's look a little bit, give you a little bit of background what the splitting means, to give you a bit of a better understanding of how the tool works and what the orange, yellow, and green means. So let's say we have this silly control flow graph here that looks like this. So we call these diamonds, so 2 diamonds in a row. And now what the tool does, in order to break the tool down, break the problem down into simpler subproblems, it just picks a node. It's called the split point, and says, what if we always took the left branch here, and then as a separate subproblem, what if we always took the right branch? Well, so it will make these into separate formulas, and if one of them is SAT, then we're done. We don't even need to look at the others. We can just return violated. So SAT result means violated in our case. And if one is unsat, we need to look at the others. And if all are unsat, we're also done. And if this splits, and we do this recursively. So if the formula here times out, then we might split further, look for another split point and go on. So actually, after splitting 3 times, we might up with these 4 subproblems, right? And if we got unsat / not violated on these left 2 and timeout on the 3rd one and queued on this last one, then the coloring would look like this. So the orange basically shows you the subproblem that we timed out on. The yellow shows you nodes that we haven't looked at yet. And the green shows you nodes that we are sure, like whatever path we took, right? So whether we go left or right on this other branching, we have a not violated answer for this. So those are the green nodes. Yeah. So this is kind of a summary of what I said. And then there are the violet nodes. I showed them already. But is there a question? Or is now a good time? I don't know.
Yeah, we have a question, which is, what are the heuristics you're using to estimate complexity?
Which heuristics? So that's a good question, and it's very work in progress. But on this, so for starters, these are them, right? So we're at the correct slide for that. So for a given node, to decide whether it's hard, we just count how many multiplications, divisions, sign divisions, modulos do we have, which aren't linear, right? Because like sometimes they just have a constant multiplication, then we don't count them. So they have a higher weight, and then we have if then else expressions. They kind of correspond to hidden branching. They also get a weight. We add it up, and we have a threshold. But this is very much falls very much under this not exact science thing, and it will grow with experience. We also have global heuristics, which is global path count. So that's actually something I'm sorry, I forgot to show, but there's still time. So when you unfold this explanation box, you get more global statistics about the whole program. So first of all, the path count. So this is on current master. The others aren't, but will be soon. So first of all, the global path count. So how many paths does this program have? So I'm not talking about feasible paths, but if you just look at the control flow, how many paths? And because the numbers get high, so this is somewhat low path count. It's 2 to the power of 27. So this I tend to look at just this order of magnitude here. And then it also breaks it down for each of your calls, how much it contributed. And then we have further statistics. One about how hard the memory and storage is. So basically the graph of the arrays we have internally. So this is more, see this more of a preview. We'll land and document this soon. And then also talking about bitwise operations and also global nonlinear stats. But for now, it's mostly the path count broken down to the whole program, but also to methods. And for each node, these counters here, how many nonlinear operations and how many if-then else's. But this will be, I'm pretty sure this will be a moving target. Also, yeah, so very much depending on practical feedback. Let me know if this didn't answer the question. We can always come back. Okay, so now I'm entering into the part with the case studies. So this is actually the first one that we, the example I just showed you, right? So we had this muldiff function, very long, pretty hard. And okay, so that's not 2 to the 7, it's 2 to the 27, sorry about that. But the path count didn't seem to be the issue. So in so my feeling is something like below 2 to the 15, let's say, is low. Up above 2 to the 60 is becoming more concerning. Above 2 to the 100 is really hard. But 2 to the 27, what we had there was okay, but we saw the nonlinear arithmetic was pretty heavy. So, and we also observed that it came from this muldiff implementation here. So what we did to mitigate was summarize the muldiff. And actually, in this case, we're kind of lucky, so to speak, that in CVL we have full precision integers. So this very smart muldiff function that gives us full precision muldiff beyond the 256 bits, you would need 512 in general for a naive implementation. So we can just summarize it with our full precision multiplication in CVL, and then the division, and then later constrained to the math end. So this has the same behavior. I mean, of course, we're assuming that the muldiff function of OpenZeppelin behaves as expected, but that would be a separate proof. We can also go about proving that, but if that holds, then this is an exact summary. We haven't changed behavior, but we've simplified the problem massively, right? So we're going from something like 30 nonlinear operations down to 6 overall, because this is called twice. So we applied the summary, and then we also changed the solvers. So especially for nonlinear operations, this yikes solver is interesting. And in order to have that activated, this SMT hashing scheme has to be set. So for now, just take these options as a bundle, right? So we'll also document them as a bundle to basically say, when nonlinear, this is a, so like you have reduced your nonlinear to a reasonable amount, still timing out, then try this option. So that's one mitigation example. Another one, so I'm just going from the, very high level view of the diagnostics. So we observed, again, moderate size due to the 25 paths, and there was nonlinear arithmetic. So this is a likely culprit. And we observed there's the scat acid price. Again, very typical, right? Again, the mul-diff pattern. Yeah, it's also very typical that you have this conversions. So, but then our colleague looked more around the code, and he observed that actually this denominator of this fraction, it is a variable, but actually it's a variable in a very limited range. So it can only take, so if you have overflow protection and you have the powers of 10, and you can't go beyond to the 256, then you only have 79 choices of this, of what this underlying assets value can actually be. And so now this is true, but however, this wasn't the constructor, right? So of the contract. So the rule didn't know about it immediately, that this is a power of 10. So it's a different story for invariance, but for rules, we have to tell that in the rules. So that's what we did. So we just added an extra constraint that is an invariant that we can also prove about the contract, and added it to the rule. And then the solvers actually got it. Yeah. So one more example. So it's even higher level, right? So sometimes there's more code. Sometimes you take your hints just from the path count. So in this case, it's the path count is in the suspicious region to the 80. And then there's the splitting, right? So I showed you how the splitting works, but there's a lot of like, which split points do you choose in which order? And how much timeout do you give before splitting again? Things like that. So we have a lot of options that configure that. And this is just a bundle of them. So there is more documentation to be added, but I can go into details. I think I want to leave room for questions, so I won't explain every single one here, but this is like a bundle to try out, and we can assist you in tweaking them one by one. Yeah, so this, for example, got solved by that. Then another example, last of my examples, is in this case we actually had a high path count. So 2 to the 200 is, so let's say I haven't seen an example where we actually succeeded on such a big problem. And we also observed kind of this shape in the control flow graph, right? So it's very redundant, and it's kind of diamonds in sequence, but a little, like more complicated diamonds. And the sequence of diamonds is always bad, right? Because you get, if it's simple diamonds, you get 2 to the power of number of diamonds passed. So we saw this, okay, this shape is very bad. So let's think about where does it come from? And yeah, so again, this is where you can see in this explanation box that this path count is so high. So we thought, where does it come from? And actually, so there is kind of a source for this, which is when some pretty complicated struct, which has unbounded components, which this has very heavily, is passed from spec to solidity, which is happening here, right? So that means that the solver has to right, it's a Havoc struct, so it doesn't know how long it is, and it also doesn't know how long each of these components are. So it kind of has to basically make up a shape of memory that fulfills these constraints. So this component one after another, but they can have arbitrary length between them. So, long story short, it makes for a very hard control flow, because this, all of this has to be copied around with loops. So we saw, okay, so this struct is passed to spec. So we kind of resorted, we went to the last resort, and we also observed, right? So not all, for the given rule, not all of these were actually relevant. So it was actually a pretty straightforward reasoning to say, we don't need these parts of the struct, only these parts are relevant. And this kind of got these huge diamonds, right? I only showed you a part of this control flow graph down to this for that particular method. So the paths, I guess we got down below to the 100 or so. Yeah, so that is also a mitigation example. Yeah. Yeah, so this is for the examples. So just to summarize high level, well, we have these candidate reasons. We'll continue to update it. We'll also publish and document it. So this is the first documentation, this public webinar. And we'll try to improve the tool feedback. So hopefully it's kind of a dialogue with the tool. And yeah, and also very soon this feature will give you live information if you want it on the console, where this extra option. This still has to land, but should be in one of the next releases. So you don't have to wait for the timeout dump. And yeah, and then when you've identified the difficulties, you can change the things that I think I had an example that kind of covered more or less these cases of setting spec in code. Yeah, so this is basically what I said, just to frame it again. So timeouts are here to stay, even if we make the tool so good that today's timeouts are all solved. It will be possible to write a rule that produces a new one. And we're working on both in-tool and out-of-tool feedback and help for the timeouts. So, and yeah, it remains a matter of experience, yeah, that we want to build also with you together. Yeah, so there are docs. They're in a very early stage, I'm warning you, but they will get better. Yeah, thank you.